Okay, so today I want to talk a little bit about compact Lie groups. So once again, I say thank you for the invitation to speak to you, and thank you especially to the organizers of this meeting. I know it's always a lot of work to organize something, and I think it's probably even more difficult at the time of COVID. So thank you very much. So I want to talk about compact Lie groups, Haar measure, to give some applications to spherical harmonics, and then I will very, very briefly touch on some generalizations of what I talked about earlier by Hermann Weyl, and a little bit about some current research. And this is a little bit preparation for tomorrow. So technically, a Lie group is a group, so something that has a multiplication and an inversion and so on. That is also a manifold. And the basic example of a Lie group is the group of invertible n by n real matrices. So I guess that this is something that we study in linear algebra. We know when an n by n real matrix is invertible and so on. So if I take the vector space of all real matrices, n by n matrices, then I can identify this naturally with Rn squared. And so this gives me a natural topology on the space of n by n real matrices, and the determinant is a continuous function on the set of matrices. And this means that this set of matrices whose determinant is not zero is an open subset. This is exactly GL and R, the invertible matrices. And the natural identity mapping from GL and R to Rn squared is a coordinate chart. So this makes it into a manifold. So it's a group and a manifold. The closed subgroups of GL and R are also Lie groups. This is a slightly difficult theorem, so I'm not going to prove it, but I'm going to mention that these include the orthogonal groups, which are called ON. So ON is the collection of all matrices that are orthogonal. So let's remember that a matrix is orthogonal if when I multiply the matrix by its transpose, U transpose times U, then I get the identity matrix. So in particular, this means that U is invertible and the inverse of U is equal to its transpose. And it's easy to see using properties of the determinant that if I have a orthogonal matrix, then the U transpose times U is the identity. The determinant of the identity is 1, so that's equal to the determinant of U transpose times U, which, because the determinant of a product is the product of the determinants, is U determinant of U transpose times determinant U, and that's equal to the determinant of U squared. So the determinant of U is plus or minus 1. And often we talk about just about the special orthogonal group, which is the subgroup with matrices of just determinant 1. So here is a useful lemma that a matrix is orthogonal if and only if when I take the columns of the matrix, so an n times n matrix has got n columns, and each of these I can think of as being as a vector. So I have n vectors, and these n vectors have to be orthonormal. They have to be of length 1, and they have to be perpendicular to each other. And this is probably something that you see in linear algebra. And in any case, if you know some linear algebra, you can check that this is true quite easily. And this makes it easy to decide whether a matrix is orthogonal or not and construct orthogonal matrices. And if we want to show that it's a manifold, then we can use this fact to construct coordinate charts. So that's some very basic facts about orthogonal matrices. Now, I'm often called an orthogonal matrix a rotation. It's mainly because rotation is shorter than orthogonal matrix, and it's easier to write and easier to say and so on. But generally speaking, orthogonal matrices are not really proper rotations, because especially in high dimensions, you can have one axis pointing in one direction and you can rotate around that axis. And then in some other variables, you can have a different axis pointing in a different direction and also rotate about that at a different speed. And then if the effect of this matrix is not really a proper rotation then. But another fact that we need to know is just to remember that if we've got two unit vectors in Rn, then there is an orthogonal matrix that takes one of them, the other one. That's not so hard to see either. Now, the orthogonal group is a Lie group. Now, there is an abstract theorem that says that on every Lie group, there is something called the Haar measure, which is unique up to constant multiples. So the Haar measure is a Borel measure. That's something that gives a measure to open sets and closed sets and so on. And it has the property that if I take any measurable subset of the Lie group and I multiply it by some element of the group, then I get a set US, the translated set, and that has got the same measure as the measure of the set. So that's an abstract theorem. It's actually true in more generality than this, and is somehow a basic theorem of measure theory. If we've got a compact group, then the measure is always finite, and it's natural to assume that the total measure is 1, which we can do just by multiplying the measure by a constant. And I'm not going to talk about the measure anymore, but I am going to talk a little bit about integrals. And when I write down an integral, as I've written down here, integral g f of u du, or f of u0 du0, then I mean an integral constructed using this measure. So this is, when you have Lebesgue measure, you can construct a Lebesgue integral. When you have the Haar measure, you can construct this integral. And the fact that the measure is invariant for translations means that when I integrate a function, if I translate the function by introducing another element of the group, then I don't change the integral. And this is true for all suitable, which means measurable or continuous or something, but I also allow vector valued functions. So this is, let me just say that there exists a general theorem. It's not too hard to prove, but it takes a while. And like many theorems in measure theory, it's a little bit long and complicated. So I'm just going to assume that this is true. Okay. I'm now going to work in Rn, and I'm going to let E1 up to En be the usual basis vectors. And I'm going to look for a subgroup of the orthogonal group. And this subgroup I'm going to call K, and it's going to consist of all the matrices of this form. So where I've written a star, I can put in anything, as long as I end up getting an orthogonal matrix. But where I put in a 0 or 1, then I have to have a 0 or 1. Now, that means that if I take these vectors corresponding to the the columns except for the last column, then they're orthogonal amongst themselves, and they're also orthogonal to this one. It's easy to see that they're orthogonal to this one, because if I take an inner product of, say, this vector with this vector, I might have something that's not 0 here, but I multiply it by 0, or I've got something that's not 0 here, but I multiply it by 0, and then I add these up to get the inner product. So the inner product is obviously 0 for these, but it also has to be true that if I look at these vectors here, then they're also orthogonal. And that means that if I forget about this bottom row of zeros and just think of these as vectors in Rn-1, then I've got a lot of vectors in Rn-1 that are unit vectors and orthogonal. These vectors in Rn are unit vectors and orthogonal. Therefore, when I just cut them down a little bit and look at these vectors here, then these are also orthogonal and unit vectors. So from the lemma that said how to recognize an orthogonal matrix, it means that every matrix like this, if I just forget about these zeros and this one, then I get an orthogonal matrix of an n by n, an n-1 times n-1 orthogonal matrix. And so this subgroup can be identified in a natural way with an orthogonal group of 1 dimension less, and so it's a Lie group, and so it has its own Haar measure. So that's a fact that we're going to use to study spherical harmonics. So now it's time for my application spherical harmonics. So if I have an orthogonal matrix, and if I have a polynomial, and this, remember from yesterday, this is the homogeneous harmonic polynomials of degree m. So P is a polynomial, it's homogeneous of degree m, and it's harmonic. Then I define pi u of P by this formula, pi u of P at x is P at u inverse x. It looks slightly inconvenient to have the inverse there, but in fact it turns out to be convenient to have it. So this means that if I start out with a polynomial P, I get a new polynomial, pi u of P, which in some sense has been rotated around. Later on, I'll have a picture of what happens when we rotate a polynomial around. Now, it's possible to do calculations and to check that this new polynomial is still homogeneous of degree m, still a polynomial of degree m, and it's still harmonic. It's basically true that if you take a harmonic function and you rotate it around, then it stays a harmonic function. So that tells me that I have a linear mapping that's acting on the space Hm of harmonic homogeneous polynomials. Now, it's also possible to check just using the definitions that if I take pi m of uv, that's the same as taking pi of u times pi of v. That's just a question of you take this, you write down a polynomial, you write down an x, and then you apply the definition. And it turns out that this is true. And the reason that we have the u-1 here is to make sure that this is true. And it's also true that if I take pi m times the identity matrix, then I get the identity operator on the space Hm. If I put in here the identity matrix, I don't I don't change x at all, so I don't change the polynomial, so I get the identity. And this means that we have an example of what is known in algebra as a group representation. Okay, so any questions? No, okay.
Maybe no.
Maybe not, good. Okay, so if I get a polynomial that's not zero, then by definition, there has to be some point where P of X is not zero. Otherwise, it would be the zero polynomial. So I can take a orthogonal matrix such that U, and this is supposed to say that U of X is equal to En. So I guess let me write down that correction for myself. I don't know whether at the end you would like me to provide the PDFs of my notes, but I'm happy to do that. But I need to make the corrections first. So
some people has asked.
I will take I take a matrix U so that U applied to X is equal to En, and that means by definition that when I take this pi of U, this operator pi of U acting on P at En, that's P of U minus 1 En, which is P of X, which is not zero. And so that's saying that if I want to, I can rotate around the polynomial P to make sure that at En it is not zero. So that's not too hard to see. Okay, now I'm going to use this. I'm going to define a linear mapping on the space of continuous functions by, well, saying that Q of P of X is the integral over K. K is this subgroup of the orthogonal group. This is the subgroup of matrices that don't do anything to the coordinate, to the basis vector En. And then I'm going to integrate pi v, this rotated version of P, against in using the Haar measure on the group V. So this is something that the Haar measure allows me to do. Then Q of P is a continuous function. And it's also true that pi of V0 acting on Q of P is equal to Q of P. That means, if you like, that Q of P is a function that somehow doesn't depend, it doesn't depend if I take rotations in certain directions. And that means that Q squared of P is equal to Q of P. And that's, I guess, says that Q is a projection. Let's notice that it's not a trivial projection by saying that Q of P is not equal to 0 if P of En is not equal to 0. And finally, if P is a harmonic polynomial, then Q of P is a harmonic polynomial. So this is a very important proposition for me, and so I'm going to give you the proof in pretty much complete detail. So the first thing is that this Q of P, I'm integrating over a collection of matrices. Now, any integral, I can think of an integral as a limit of sums. Think of a Riemann integral. The first time that you study integration, you usually study what happens when you divide the real line up into intervals and then take a value of the function at points in each of these intervals. If we do that process here, then we divide K up into little pieces. We take an element out of a V, a matrix P out of this piece. We apply that to our polynomial or our function P. And then we multiply by the size of the piece of the orthogonal group that we're taking, and we add these up. We're getting a linear combination of these objects, a linear combinations of functions that are sending x to P of V minus 1x, because this is what this pi m is doing. Now, each of these functions is a continuous function. And so I'm taking a linear combination of continuous functions, and so I get a continuous function. And the integral, when it exists, well, normally we just take a regular limit, but here I'm taking an integral, a vector-valued integral, an integral in the space of continuous functions, and the limit exists in the space of continuous functions. And this limit of linear combinations is a uniform limit of continuous functions, and therefore it's a continuous function. So this tells me that Q of P is a continuous function. So that's, I guess, vector-valued integration. The next thing to notice is that in the particular case that the P is a harmonic polynomial, then all of the pi m v of P's, all of these things that I'm integrating together are also harmonic polynomials. So I'm taking linear combinations of harmonic polynomials, which are still harmonic polynomials, and then I'm taking a limit of these, and for similar reasons, this is a harmonic polynomial. So I've proved the first bit, and I've proved the last bit. Now, the next thing is to prove that if when I look at Q of P and I apply one of my rotation operators, then I don't change Q of P. So let me see if I can do that. I have to write down what this is by definition. And by definition, that's pi m v0 applied to P. But I have to translate by pi m v of P. I have to translate by v0 to the -1 because pi m of v0 brings in a v0 to the -1 times x. So this is this, and then the QP is this bit with the integral pi m v of P integrated with respect to v. Now I apply what is the definition of this? Well, this brings in another v to the -1. Now v to the -1 times v0 to the -1 is actually the same as v0v all to the -1. So I can take that out as pi m of v0v px dv. And now I use the fact that my Haar integral does not depend on translations. So I'm integrating, this is my variable that I'm integrating over, and here I'm effectively translating the variable by v0. But I get the same answer if I remove the translation by v0. So I get this answer here, and that is QP of x by definition. So when I take this QP, then it's something that when I act on by v0, nothing happens. So that means in particular, if I apply Q again, I apply all of these things and then I integrate again with respect to these V0. But if I'm integrating over K, these translated versions or these rotated versions of QP, but each of these is just the same as QP, then I'm just integrating QP. I've normalized my Haar measure to have mass 1, so this is just QP of X. So that says that Q is indeed a projection. And now last, if the polynomial is not 0 at En, then by definition, QP at En is the integral of P of U minus 1 En. Now, U, let me just go back, is a matrix like this. When I apply it to En to the nth coordinate vector 0, 0, 0, 1, I just get 0, 0, 0, 1. So this is the same as En. And so that's P of En. And that I assumed was non-zero. So I'm getting a new function, a new polynomial that is not 0 at En, so it's not a 0 function. So let me go to the next page. We have constructed a mapping U, a linear mapping U, and shown that it's a non-trivial projection. Okay, so now I'm going to show that it's projection onto a one-dimensional space. So I'm taking a polynomial in HM and I'm applying Q to it, and I want to show that this lies in a one-dimensional space. Well, how do we show that a function lies in a one-dimensional space? We have to show that all the functions, all the possible functions that we can get are all multiples of each other. So we have to say something about this function. So here's the first step. If I have any vector x in Rn, then I can write it as x prime times xn, where x prime is just x1 up to xn minus 1. So I'm just leaving out the last coordinate and putting it separately. Now, QP of x prime xn, this only depends on the modulus of, on the length of x prime and on xn. So why is that? Well, that is because I know that this QP has the property that when I act on it by a matrix D0 in K, it doesn't change. And I know that when the matrices in K are like this. So when I act on the variable by a matrix of this form, the value of the function doesn't change. Now, when I act with matrices like this, I can, if I take the components except for the last component, I can move them around however I want. So that I can, if I get two vectors of the same length, I can move one to the other. And so the function that has this property can only depend on the length of the vector. So that means that QP of x prime xn can be written as some sum, it's a polynomial after all, of constants, and then the length of x prime to some power, and then xn to some other power. So I'm writing it out as a polynomial, but I'm just saying that the way that it depends on this variable is just depending only on the length. Now, if this is going to be a polynomial, actually, I have to take the length squared or the length to the fourth power or so on. That is a polynomial, but the length itself is not a polynomial. So that means that these coefficients have to be 0 when j is odd. So we can really think of this as being a sum where I've only got even powers. Now, since the vector x is made up of x prime and xn, then the length of x squared is equal to the length of x prime squared and plus the length plus mod x plus xn squared. So x prime squared is actually the length of x squared minus xn squared. Now here I've only got even powers, and so that means that if I replace this by this, and then expand out if I want to, I end up getting that q of px is a polynomial in the length of x squared and in xn. And xn is just the inner product of x and en. So I know something about what QP has to look like, but I don't know enough. But the fact is that I'm dealing with harmonic polynomials. And because I'm dealing with harmonic polynomials, I can use the fact that the Laplacian applied to this polynomial is 0. So now I do another calculation. I use the fact that the Laplacian of QP is 0. So 0 is equal to the Laplacian applied to QP. I know it has this form. This should be x prime rather than x, but I'm sorry about that. So if I apply the Laplacian to this, so this is x prime, which depends on x1, x2 up to xn minus 1. So the derivatives respect to x1, x2 up to xn minus 1 are applied to x prime. But they don't affect xn because that's the way that partial derivatives work. On the other hand, the last second derivative in the Laplacian is the partial derivative with respect to xn squared, and that one acts on the last part of the polynomial, the xn to the m minus j. So I can work out what this comes to. And when I work out what this comes to, it turns out to be the sum of the coefficient Cj that I had already. Applying the Laplacian to the length of x to the j gives me j times j plus n minus 2, length of x to the j minus 2. That's a not too difficult calculation. And applying the ddx n squared to xn minus j gives me m minus j minus 1, xn to the m minus j minus 2. So now I know that 0 is equal to this sum. Now, I haven't done this, but I could, or you could if you wanted to, you could change the label j to be j plus 2, and that would change this, and it would change that, and it would make mod x to the j minus 2 become x to the j, and xn to the m minus j become xn to the m minus j minus 2. And then I could put these two things together, and then I would end up getting a single sum that has to be 0. And the single sum of this form that's going to be 0 means that all of the single pieces in it have to be 0. So that means that there is a relationship between these coefficients, and that relationship means that if I know what is C0, then I know automatically what is C2, and then I know automatically what is C4, and I know automatically what is C6, and so on. Or, yes, J is always even, so I only have to worry about 0, 2, 4, and so on. So just knowing what is C0 tells me what all the other coefficients are, and that means that QP is determined by just one real or complex number, and that means that the dimension of the space of these things is 1. So that, I guess, is a proof of that fact. Now, I'm going to choose one particular function in this space, and I'm going to choose it so that when I evaluate it at En, I get this number here, the dimension of Hm divided by omega n minus 1, which is the measure of the unit sphere in Rn minus 1. That's just a choice, but it's a good choice. So in the proof above, we saw that QPX was a polynomial in norm x squared and xen. That means if I consider this, which is a particular case of these, this is a polynomial on the unit sphere. Mod x squared is always equal to 1, so there's sort of nothing, this doesn't do anything. And so this function here is actually a polynomial in x inner product En. We call it a zonal spherical harmonic. So I say up to normalization, this is the function in Hm that is most concentrated near En and near minus En. Because I'm dealing with homogeneous polynomials, they're always either odd or even. And so if it's not 0 at En, it's also not 0 at minus En. That has to be true. And now, if I take a different point in the sphere, I decide Zmp to be pi mu to be the rotated version of Zm at En, where u of En is equal to p. And this one was a polynomial in xen, and this one is a polynomial in x inner product p. So here's a picture. I'm afraid it's not very good. I'm not very artistic. So here is the sphere, and in gray, I've tried to draw in the graph of this zonal spherical harmonic. It's something that it's quite concentrated. It's concentrated close to this pole and to this pole. It's supposed to be even, so the value here is equal to the value here. But whether it's even or odd depends on the degree of the polynomial. Then I can choose another point P on the sphere, and I can get another function Zm with a P, and that's what I get by taking this function and defined on the sphere and rotating the sphere around so that the part where the function is most active is at P. So this is a picture of Zm at P. Okay, now here is my big theorem for today. If F is in L2, then F is the sum of projections applied to F. Each projection gives me a harmonic polynomial, and it's given by the formula integral over Sn minus 1, F of P, Zmp of x dp. So here I'm taking, if you like, a limit of sums of these zonal spherical functions in x, and I'm weighting the different zonal spherical functions with the point P, and that is going to give me an orthogonal decomposition of F, but it gives me a nice integral description of the projection. And the proof involves a mixture of ideas from group representations and Hilbert spaces, which is like the proof up here. So first we have to check really that this is an orthogonal projection. Well, if we know that this is an orthogonal projection, then everything else is going to work out okay. So from the formula for the zonal spherical function, we can check that ZMXP is ZMPX. That's essentially because this is a function of the inner product of P and X, and the inner product of P and X is the same as the inner product of X and P. So that says that if I have something that is a spherical harmonic of degree L, this coincides with the spherical harmonic of degree M, and the spherical harmonics of different degree are orthogonal to each other, so I get 0. So that's looking like an orthogonal projection. The other thing is that I have to check that it's really a projection. I have to check that PMF is equal to F. And for this, I use a nice idea. We restrict the inner product, or the L2 inner product, just the integration over the sphere, just to the space of harmonic functions on the sphere. And I note that if I just evaluate at a point, because I'm dealing with polynomials, I can certainly evaluate at a point, and it's going to be a bounded linear functional on the finite dimensional Hilbert space. The space HM is finite dimensional. We even calculated its dimension. And so because it's finite dimensional, all linear functionals are continuous. Now, the Rees representation theorem tells us that there is an element of this Hilbert space, so that f of p is equal to f inner product wp of m. And it's enough to check that wp of m is equal to zp of m for op, because that then tells me what I want. So first of all, we consider the effect of rotations, and we can see that Wm at P is what happens when you take Wm at En and rotate it around. Now that's exactly the same thing as happened with the zonal functions. And so if Wm at En is Zm at En, then after rotation, Wm at P is Zm at P too. So then we have to check that the Wm at En, this should be W, which should have the En up. This doesn't depend on these in the special subgroup K that we had before, which means that Q of Wen is Wen, and that means that this has to be a multiple of Wen. And then last, we have to check that the multiplying factor is 1, and there's another argument to do that, but I'm going to leave that out. So that's my big theorem. My big theorem says that I can write down quite explicitly formulas for the projections in this space of spherical harmonics. And the formula ZPM is given by some series that I can, if I want to, I can calculate explicitly. And in fact, I know that people who do numerical analysis actually do that. They calculate it explicitly and they use it. So now I'm just going to summarize very quickly a generalization of this that is mostly due to Hermann Weyl. So the theory of spherical harmonics in 3 dimensions was developed in the 1800s. This has names of people like Legendre and Laplace and so on associated with. But there was a theory of spherical harmonics in higher dimension that was developed by people interested in physics, and that was in the early 1900s. On the other hand, the theory of Lie groups began in the late 1800s and grew a lot in the 1900s. So a very big generalization of the theory of spherical harmonics is due to Hermann Weyl. He developed a theory of representations of this group. We saw that the action of rotation groups on spherical harmonics is what is called a group representation, and he developed the theory of group representations greatly to deal with this. He started with just some examples of orthogonal groups and spherical harmonics and ended up doing this for quite general compact Lie groups. So here are a few key aspects of his theory. So every compact group has got a maximal torus, which is essentially unique. Maximal torus is a closed subgroup that is isomorphic to a direct product of a certain number of copies of the multiplicative group of complex numbers of modulus 1. If you take two complex of numbers of modulus 1 and multiply them together, you get another complex number of modulus 1. Or if you like, it's a group of 2 by 2 matrices with cos theta, sine theta, minus sine theta, and cos theta. In the case of the orthogonal group ON, this is just a subgroup of a suitable subgroup of block diagonal matrices. And then there are formulas for integration on G that reduce to integration on T. So we did some integration on compact Lie groups. If this can be reduced to integration on a torus, and an integration on torus is something that we more or less know how to do. So here are the main points of his theorem. Every compact Lie group has got a well-determined collection of irreducible representations. I call the irreducible representation pi lambda. This is on a finite dimensional vector space H lambda. These generalize the representations that we considered. The parameters lambda are in a certain cone in a lattice. They're discrete parameters and they lie in a nicely described set. The dimensions of the space of the representations and their characters can be given explicitly, and the characters can be used to describe the projections, much as we describe the projection in the space of zonal spherical harmonics. Last, harmonic analysis on G associates to a function f on G, a family of operators on spaces H lambda, and there is something that we call the Poincaré theorem that says that the inner product of functions on the group is a sum over the different representations with a weight that's equal to the dimension of the representation, which we know exactly, and then the trace of the product of two operators. One is an operator associated to F, and the other is an operator associated to G. So there is a theory of harmonic analysis in this context due to Weyl. And so let me just end up saying that currently, if we take a compact Lie group that's not an orthogonal group, then there are generalizations of Laplace-Beltrami operators and so on, and the eigenvalues and eigenvectors can be calculated explicitly. And compact Lie groups different to ON can be used to look at other kinds of geometry. For instance, there is a kind of geometry called contact geometry, and the unitary groups can be used to study these. So currently people are proving theorems about more general Lie groups that can be applied to different kinds of geometry. And that's something that I want to talk a little bit about next time, but mainly I want to look at explicit examples like zonal spherical harmonics and the sphere and so on. Okay, thank you.